This video will be about applying the compound interest formula. So first we're going to focus on what most people think about when we talk about compound interest. So we have our compound interest formula. A of t equals P times 1 plus r over n raised to the n times t. Now, what these values mean, A of t is the amount in the account after a specified number of years t. P is the principal, or the initial value. R is your annual rate, expressed as a decimal, so do be careful there. N is the number of times you compound each year. So if I say I'm going to pay you quarterly, that means it's going to happen 4 times a year. And t, of course, time in years. That should be all the values there. So let's jump into an example where we plug this in, see how it goes, and see what we get back out. An initial investment of $10,000 at an interest rate of 2% is compounded monthly. What will the investment be worth in 30 years? So first, let's write down some of the things we know. The initial investment is $10,000. R, the interest rate, is 0.02. N, it says compounded monthly, so that's 12 times a year. And then they're telling me T is going to be 30 years. Alright. From here, it looks like I have all the values for this formula to plug in and get an amount back out. So, A of 30 equals 10,000. 1 plus 0.02 over 12 to the 12 times 30. Alright, so here's where WebAssign is going to get picky with you. I would suggest typing all of this into a calculator at once in order to get the correct answer. So, if we type it all in at once, the amount after 30 years will be 18212.09. So $18,212.09 will be the amount in the account after 30 years. Now, that's $812.09. $8,212.09 that you didn't work for. So compounding interest is nice if it's your friend, not so nice if it's on a credit card. So beware. Now, our goal from there, we've compounded normally. But what happens if we want to compound all the time, every second of every day, at all times? We want to be compounding interest and things of that nature. Well, that's going to require something we call Euler's number. It's the letter E. You'll see it a few times. Now, what we can do to get to this number is the same thing Euler did. And yes, that says Euler. I didn't name him, so I got nothing for you. What we want to do, though, to get this number is as n approaches infinity. So as n gets really large, the compounding number gets really large. This value here, so this guy is going to head toward E, which is approximately 2.718282. Now, it's a decimal that doesn't end, and the further you go within, so if you put 1,000,000 in, you're going to get a more accurate version. If you put so on and so forth, 1,000,000,000, trillion, so on, you're going to get more accurate. But we head toward this number e, and e is what we use if we want to compound continuously. Because if it were just days, it'd be 360 due to banking years. But since n is heading toward infinity, it's getting massive over time. Here, you're just compounding continuously or all the time, every second of every day, so on and so forth. So we head toward this, and the new formula they're going to give you is going to be, for continuous compounding, growth and decay. A of t equals p e to the rt. Some people like to call it PERT. They have the same values as before. Now, what we want to do is look at this next example. So, $10,000 is invested into an account that compounds continuously at a rate of 2%. What is the amount after 30 years? So, let's see what the power of continuous compounding is compared to our monthly. So we want A of 30 equals 10,000 e to the 0.02 times 30. Now, that 30 is going to give us $18,221 now, and 18 or 19 cents. It's 0.188. So your bank probably wouldn't round up. I'm going to round up for you so you can have an extra penny. But that's an extra, maybe what, $8 or so? So that's continuous compounding. That's normal compounding. We also have to worry about growth and decay, and that's really simple. So you're going to grow when the rate is positive. You're going to decay when the rate is negative. Okay, that makes sense. That's a typical thing. And this comes to dealing with half-lives and things of that nature, like how fast will an element decay. This is probably used with carbon dating and things of that nature. But that brings this video to an end.